The formation of complex ions is another example of equilibria. If you think about your Le Chatelier lab, you realize that you were doing some equilibria there, and in some of them you were changing forms and so on. Here we have an example where something had this form, but when ammonia was added to it, it replaced these 6 with 4 ammonias instead. So it kicked out the 6 waters, the hexahydrate, and became a I don't even know, man. We do need definitions. There's something called a coordinate bond. So that's a covalent bond, and it's when an anion or a molecule donates a pair of electrons to another ion or molecule. Oh my gosh, donating a pair of electrons? Well, my goodness, that sounds like Lewis acid-based stuff, right? Because one is donating a lone pair, and the other one is accepting the lone pair. So you have your base that's donating it and your acid that's accepting it. Complex ions are an ionic species where you have a metal ion in the center, and it's bonded to one or more Lewis bases, which serve as ligands. When we mention this word ligands, we're always talking about a Lewis base on the outside bonded to a central metal ion. And here we have an example here. If we had nickel and there are 6 of these waters attached to it, overall it will have a +2 charge, but there's 6 water ligands surrounding the nickel. Oh no! If we have another example of equilibria, we need another value of K. One more. Oh, good gosh. Formation constant. So we're going to use F as the subscript, K sub F. And it will describe the formation of a metal complex from a free metal ion and its ligands. So here we have a copper ion. If there's ammonia around, it will form a nice copper with the 4 ammonias around it. What would be the KF for this? Well, we'll always do what we do before. We put the products on top. Well, there's only one product. There it is. I want to know what its concentration is. And in the denominator, we're going to put the reactants. Here's the copper. There it is. Concentration of this copper. And then there are 4 of these ammonias. So the concentration of ammonia has to be raised to the 4th power. You can go look up what the KF is. You'll find out it's 10 to the 13th for this particular substance. It says that we have some information given to us about initially. Oh boy, initially. That kind of implies I'm going to use a rice table, right? Okay, well, I'll write it down. Rice table. So the reaction they've given to us, that's nice of them. That's a silver ion. And it says that I have ammonia in equilibrium with silver and ammonia attached to it. It also gives you a value for KF, 1.7 times 10 to the 7th. So we have that. And then it says initially it's 0.1 molar in silver nitrate. Well, the silver nitrate is soluble because nitrate makes it soluble. So that means it's really 0.100 molar in silver ions. Then it says 0.8 molar in ammonia. Okay, so 0.8 molar in ammonia. This is the opposite side, and this was 0. Well, we know that this is going to shift to the right. We can tell because KF isn't 0, right? So it's got to go this way. So this is going to come into existence. And for it to come into existence, some of this has to be used. One of these makes one of these, so minus X. But it takes 2 of these to make one of these. So this will be minus 2X. When you go to the what it is at equilibrium, you're like, oh dear, this is awful. This is truly awful. I'm going to end up doing all this, And I'm not very happy about this. No, don't make me do this. You know what though? Look at that KF. The KF times 10 to the 7th? That's huge. And the only way that can happen is if the numerator is really huge, right? Because we know how to make this KF. It's going to be that silver with the ammonia around it, which was X, over these two, 0.100 minus X and 0.800 minus 2X. X has got to be quite large. So this is essentially going to go to completion. Now, what limits it? That's what I have to think about now. I can look over here at these and say, one of these is going to limit it. If I run out of this, it would imply that X is 0.100, or really, really close to it anyway. If I run out of this, it would imply that X is 0.400. Well, I would run out of this before that ever happened, right? We get to 0.100 being used before I would get to 0.400 being used. So I can say that X is going to be approximately the whole darn 0.100 molar. Well, if that's true, I can maybe do something about this. What is this? Instead of doing this, because that would end up, if I did that, I'd say I'm dividing by 0. That's not a good idea, right? So I think I'm going to have to do something about this. I need to rearrange this. Let me rearrange it in terms of what these were, because if you'll recall, this came from this one. This ended up here, and this ended up there. Oh, goodness, you know what I didn't do? Oh, I didn't square that. If that's there, it needs to be squared here. Let me write down what I think they are. I think that this one is essentially going to go to the 0.100. I think that I had better just say that this is the silver, so I don't get myself in trouble. It's going to end up being very small because almost all of it will disappear. And then here, because I'm saying that X is almost exactly 0.100, then I should say that this is going to be 0.800 minus 0.200. That would be 0.600, but it needs to be squared. When I square it, it's going to be 0.36. That's approximately correct. 0.36. Close enough, anyway. So I have a number here. I have a number here. I have a number here. And this is the only one that is missing. Okay, let's rearrange it. I want to know what this is. If I bring it up like this, I'll have to take this one down like that. This is all algebra, and you'll have to sit there and look at it, do it yourself so that you don't goof it up. But now it's all numbers, and if I run it through the calculator, I'm going to end up getting 1.6 times 10 to the negative 8. That is low. So what it's telling you is that essentially if the silver meets ammonia like that, it's all going to end up becoming the polyatomic ion here. And that's what this is also telling you. Oh, yeah. Notice, you do not have to do this section on hydrated metal ions.